So we now turn to looking at triangles in hyperbolic space. We actually briefly already saw ideal triangles. We'll see ideal and not so ideal triangles now. They're both very important for constructions in hyperbolic geometry, and we'll also mark our transition to geometric group theory. So here are a couple of examples. There are angles alpha, beta, and gamma for the triangles. Well, what do we know about the angles? First thing we know is that alpha, beta, gamma are greater than or equal to 0, but they may be equal to 0, unlike Euclidean space. In this picture, these two are equal to 0. So beta is 0, gamma is 0. And the reason for this is, as I mentioned briefly earlier, if we look at the tangent lines to the circles at this point, both these circles are perpendicular to that, and so they must be tangent to each other. So the second thing we know is that an angle equals 0 if and only if the corresponding vertex is ideal. So this is the first thing we know. And the second thing we'll see, we're just taking a simple picture. Here we have these sort of curved lines, which are chords, arcs of circles. And what I've drawn are the straight lines, which is the Euclidean one. Well, I mean, it's quite clear, and you can just check from the definitions with a little care, that the hyperbolic angle, this, is less than Euclidean angle. And the Euclidean angles add up to pi. So alpha plus beta plus gamma is strictly less than pi. In fact, at the extreme for ideal, they're all 0. So it lies between 0 and pi. So each of them is a non-negative number, and they add up to pi. So this is what we know. Well, the first main result here is about hyperbolic geometry, triangles in hyperbolic geometry, is that suppose we are given alpha, beta, gamma greater than or equal to 0, pi minus, okay, I'll write it that way, pi minus alpha plus beta plus gamma is also greater than or strictly greater than 0, then there exists triangle, okay, I'll call it delta alpha beta gamma, unique up to congruence, with these angles, with angles alpha, beta and gamma. Now there are several remarkable things. Of course, in Euclidean space, angles don't determine a triangle up to congruence. They determine it only up to similarity. Yeah, so that is a major difference. Otherwise, we have a statement similar to the Euclidean one. So once you know the angles, you know the triangle. And any angle subject to only the restrictions we already saw is permissible. Any triple of angles is permissible. So let's see how this goes. So by symmetry, we can take, so we look for a triangle PQR. And here's already a picture. Okay, and without loss of generality, let's say P equals 1 and Q belongs to the imaginary axis IR. Q with P equals I. So I'm using the upper half plane model. Okay, so this is the point I, and I've drawn it. So I've drawn an angle alpha here. Okay, so this is the angle alpha here, where is P, and we have a vertical line passing through that. Well, what happened if I take a point Q. Let's first start with a point Q here, which is Q minus 1, and take an angle beta. Now in the Euclidean situation, what happens always is that if we have a line and we have two given angles on it, okay, alpha and beta, now these eventually meet at a point, okay, so these meet if and only if alpha plus beta is strictly less than pi. So that's sort of extension of the parallel postulate. But in hyperbolic geometry, you see that's not true. Here alpha plus beta is visibly less than pi. However, if Q minus 1 is very far away, well, then what happens to So we get a little circle here. I mean, this is supposed to be a semicircle. This is a hyperbolic geodesic. With these being right angles, they don't look that way. And if Q is very far away, well, they just don't meet. They go and each of the geodesics goes and hits infinity before they meet each other. So in this case, there is no triangle. Okay, so that's not very visible. So in this case, there's no triangle. Well, if we take Q closer and closer, at some particular point Q0, we get R is ideal vertex. So these meet in some sense, they meet at infinity. So that we'll get an angle which is 0 here. Gamma is 0. Okay. And now suppose we start moving from Q0 to P. So what have we seen here? That so beyond Q0, there is no triangle. Okay, so by construction we have fixed alpha beta and trying to figure out what gammas we get. Okay, in the Euclidean case we get a unique gamma. Okay, that's always pi minus alpha plus beta. Okay, at Q equals Q0, gamma equals 0. And what happens at the other end? Well, at the other end, this is a fact which you can see in many ways, but at the other end, when we are here, okay, somewhere some Q here, what happens as Q approaches P? Well, triangle approaches Euclidean, which means that gamma goes to pi minus alpha plus beta, okay, which is the Euclidean situation. So gamma starts off with 0 at Q minus 1, and as you approach here, it hits the Euclidean situation. Okay, so this equation incidentally can be written as pi minus alpha plus beta is strictly greater than 0. Okay, and then we also have, of course, gamma. So this is supposed to be gamma. So as Q approaches the triangle, gamma approaches pi minus alpha plus beta, okay, which is the corresponding Euclidean angle. And in fact, as Q goes from Q0 to P, gamma of Q is monotone. Now this is a fact of a sort which is very important in hyperbolic geometry. Lots of convexity properties and so on come from these. But I'm not going to prove these things. You should look at the calculation. So what happens to the angle gamma? If I take any intermediate position, you see it's not difficult to see that we'll get another triangle. If I took gamma somewhere here, for example, again making the angle beta. Okay, so if I took Q here, okay, I would get some angle, and this angle I can call gamma of Q. Fine. So this is the situation we have. So what happens is that at some point you end up with 0, and as you approach P you end up with a Euclidean angle, and in fact you steadily increase between the two. So then given any value of gamma, we are given gamma which is greater than or equal to 0, and gamma is oh sorry, I wrote this equation wrong. I want to take gamma to the other side. So gamma is less than pi minus alpha plus beta, and greater than or equal to 0 is in the other case. So gamma takes the value 0 and it approaches pi minus alpha plus beta. So it takes every value in between exactly once. And our choices of putting the P at the point I and the axis as the vertical axis are exactly the choices that fix the symmetry. So this is the first. So from this we see that hyperbolic triangles are exactly described by their angle.